we are going to talk about the conservation of angular momentum as it applies to orbits. So here I have a picture of the Earth's orbit around the sun. This is not drawn to scale by any means. The sun is not to scale with the Earth. The Earth's orbit is not this elliptical. If we were to draw it on the page, you wouldn't even be able to tell that it was an ellipse. So this is not to scale. But for argument, for the sake of just making this argument, we're going to use this equation. So we're going to think about Kepler's second law. Kepler's second law says that if we have a line segment joining the planet and the sun, it's going to sweep out equal areas in equal time intervals. So this line from here to here, if the Earth were to move from here to maybe here in a month, and then from here to here in a month, this area would be equal to this area. So that tells us that when the Earth is closer to the sun, it moves faster here. And here it moves more slowly. So when we're closer to the sun, we're moving faster. When we're farther away from the sun, we're moving more slowly. Momentum has to be conserved here. So this is angular momentum. It's how we're going to treat this. Initial angular momentum has to equal final angular momentum. So the angular momentum here has to equal the angular momentum, here, at any place in the orbit. So we would determine that by doing I initial times omega initial, and that's equal to I final times omega final. Now we're going to treat, for I, we're going to use mr squared. So mass of the Earth is constant, but the radius is not constant. So m times r initial squared times omega initial, which we could also do as v initial over r initial, is equal to mass times radius final squared times v final over r final. So we can see that one of our radiuses cancels, and we're left with the statement mass times r initial times velocity initial equals mass times, and mass cancels. Oops. Okay, so we're left with r initial times velocity initial equals r final times velocity final. So we are going to apply this in a problem. This is a long AP problem. We're not going to do the whole thing today. We're just going to do parts B and C. So we have a satellite orbiting the Earth, and it gives us a bunch of things here. We know that the mass of the satellite is 1,000 kilograms. We know that the radius at point A is equal to 1.2 times 10 to the 7th meters. We know the radius at position, I misread that. We know that the velocity at position A is equal to 7.1 times 10 to the 3rd meters per second. So part B here asks for the magnitude of angular momentum. And so to do that, we are going to just do L equals I times omega. And we know that I is equal to mr squared because we're treating the satellite as a particle, and omega is v over r. And one of our r's cancels. And we're left with m times r times v. So we plug in numbers, and we get 1,000 kilograms times the radius, which is 1.2 times 10 to the 7th meters, times the velocity, which is 7.1 times 10 to the 3rd meters per second. So then when we multiply that out, we get 8.52 times 10 to the 13th kilogram meters squared per second. And then part C says later the spacecraft is at point B on the opposite side of the Earth, and the new radius is 3.6 times 10 to the 7th meters. And we need to determine the new velocity. So we're going to use our moment of inertia, our rotational momentum conservation. So rotational momentum at A should be equal to rotational momentum at B. So mass times radius A times velocity A equals mass times radius B times velocity B. Now I just kind of skipped this step right here because I already did it once in this problem where I derived the equation for the rotational momentum of a particle. And so I'm just using that equation right there. Now we can see that our mass cancels, and we are left with VB is equal to RA times VA over RB. And so we can plug in numbers. 1.2 times 10 to the 7th meters times 7.1 times 10 to the 3rd meters per second, all over 3.6 times 10 to the 7th meters. And we get 2.37 times 10 to the 3rd meters per second. So we can see that it does go slower at position B. So these problems are not hard by any means. It's a pretty simple math. The hardest part is remembering that this is a thing. Because when you get a problem on an AP test and you see the orbit, you're immediately thinking about universal law of gravitation, and you're thinking about a lot of times circular motion. And so it's hard to remember that angular momentum is conserved, especially because this is a particle. So you don't really think of the thing as being rotating, but you can use the angular momentum of a particle to figure out the velocity at different points in the orbit.